In this module, we discuss the kinetics of second-order reactions. Now, we will explore the rate laws of second-order reactions. We consider a second-order reaction of two molecules of reactant A, two products. Its rate law is given by the reaction rate V being proportional to the square of the concentration of the reactant A, denoted as C. Considering that the stoichiometric coefficient of A in the reaction is 2, the reaction rate is equal to the negative 1/2 the derivative of C with respect to time. Combining these equations, we obtain a differential equation that describes how the reactant concentration C changes over time. Further, we separate the variables C and T and obtain the following equation. Negative dC over C squared equals 2k dt. On the right side of the equation, we integrate 2k by dt from time 0 to the time t and obtain 2kt. We integrate the expression on the left side of the differential equation, negative dc over c squared, from c0 to c. Here, C0 denotes the initial concentration of the reactant at the reaction start. The indefinite integral of the expression on the left side of the differential equation is equal to 1 over c. Its definite integral from C0 to c is given by 1 over c minus 1 over C0. Combining both integrated parts of the differential equation, we obtain the integrated rate law for second-order reactions where one reactant is involved. It tells us that the inverse of the concentration at time t minus the inverse of the initial concentration is equal to 2 times the rate constant k multiplied by the time t. From this, we can rearrange the terms to express the concentration at any time t as 1 over 2kt plus 1 over c0 or c0 over 2 c0 kt plus 1. The second form of the integrated rate law allows us to calculate the concentration of the reactant at any point during the reaction, provided we know the initial concentration and the rate constant. This figure illustrates the decrease in the reaction concentration over time, as described by the integrated rate law. With a higher rate constant, the reactant concentration decreases faster. By rearranging the first equation, we can show that for second-order reactions of one reactant, the relationship between the inverse of reactant concentration and time is linear. This linear dependence, with a slope of 2k and an intercept equal to the inverse of the initial reactant concentration, is a linearized rate equation for second-order reactions of one reactant. Using a plot of the inverse of reactant concentration against time, we can determine from experimental results the rate constant of a reaction and the initial concentration of reactant. The half-life for a second-order reaction can be derived from the integrated rate law. By setting the concentration at half-life to half of the initial concentration C0, we can express the half-life as 1 over 2k C0. This relationship indicates that the half-life for a second-order reaction is inversely proportional to both the rate constant and the initial concentration. The latter distinguishes them from first-order reactions, where the half-life is independent of the initial concentration of the reactant. As a result, a higher initial concentration of the reactant will lead to a shorter half-life. Conversely, at lower concentrations, the reactant will persist longer, leading to a longer half-life. This characteristic is particularly relevant for substances that degrade through second-order reactions, including certain environmental pollutants, which may remain in the environment for extended periods at low concentrations. And now we will discuss the kinetics of second-order reactions involving two different reactants, A and B. Each of them undergoes first-order kinetics with respect to their concentrations, with the overall reaction order being equal to 2. The rate of reaction V is directly proportional to the product of the concentrations of A and B. We denote initial values of the concentration of both reactants as the concentrations of A0 and the concentration of B0. Importantly, for the following derivations to be valid, they should be unequal. If this is not the case, the differential equations for their concentration should be solved in the same way as it is done for the second-order reaction of the same reactant considered before. As the reaction progresses, the concentrations of A and B decrease at an equal rate. This is a consequence of the stoichiometry of the reaction, where one molecule of A reacts with one molecule of B to form the products. This equal rate of decrease is expressed by the equation V equals negative d concentration of A by dt and equals negative d concentration of B by dt. It is also equal to the derivative of the extent of reaction xi d xi by dt. At any time t during the reaction, xi equals to the decrease of the concentrations of A and B from the initial values. To obtain an integrated rate law for second-order reaction of two different reactants, we equate two expressions for the reaction rate and integrate the resulting differential equation. This is beyond the scope of this module. The integrated rate law for a second-order reaction involving two different reactants, A and B, is presented here. This equation is key to determining the progress of such a reaction. It equates the natural logarithm of a ratio involving the initial and current concentrations of A and B to the product of the difference in their initial concentrations, the rate constant, and time. The calculation of the extent of reaction xi as a function of time, according to this equation, might be complicated. Practically, it might be easier to calculate time as a function of the extent of reaction or, equivalently, of the current reactant concentrations. The same equation, in fact, represents the linearized concentration-time dependence for a second-order reaction of two different reactants. By plotting the left-hand side of the equation against time, we should obtain a straight line if the reaction follows second-order kinetics with two different reactants. This linearized relation is also useful for determining the rate constant K from experimental data. Note that, unlike reactions with a single reactant, the concept of half-life for reactions with different reactants is meaningless. If A and B start with unequal concentrations, they won't reach half their initial values simultaneously. This is a specific aspect of reactions with different reactants.